Hello and welcome to today's session. This session focuses on Learning Outcome 1 LO1, understand a range of essential data structures. In this video, you will explore key data structures and their role in algorithm design and performance. You will learn how different data structures affect efficiency, memory usage, and overall computational effectiveness, and why selecting the appropriate structure is critical when solving problems in computer science. This module introduces data structures, algorithms, and computational complexity. You will explore linear and nonlinear structures like arrays, graphs, and trees. Understand time and space complexity as core algorithmic considerations. Learn popular algorithms for sorting, searching, and pathfinding. Gain practical skills in writing pseudocode and debugging algorithms. Data structures organize and store data for efficient access and processing. The right choice impacts performance, memory, and ease of implementation. Core structures include arrays, linked lists, stacks, queues, trees, graphs, and hash tables. Each has unique strengths and weaknesses. Understanding these allows developers to select efficient solutions. Arrays store elements in contiguous memory locations of the same data type. They have a fixed size, allowing direct access via an index. Arrays offer constant time access, making them fast and memory efficient. However, resizing is difficult, and insertion or deletion is slow. They are ideal when element count is known. Linked lists consist of nodes with data and a reference to the next node. Types include singly, doubly, and circular linked lists. They allow dynamic sizing and efficient insertion and deletion. However, access is slower than arrays due to sequential traversal, ideal for frequently changing data. Stacks follow the last-in, first-out principle. Core operations include push, pop, and peek. They are simple, fast, and useful for managing temporary data. However, they have limited access to elements. Commonly used in function calls, undo operations, and expression evaluations. Queues follow the first-in, first-out principle. Core operations are in queue and dequeue. They ensure fair processing order and are efficient for task scheduling. However, direct access to middle elements is not possible. Used in task scheduling, printer spooling, and customer service systems. Trees are hierarchical structures with nodes, including a root and children. Types include binary trees, binary search trees, AVL trees, and heaps. They offer efficient searching, insertion, and deletion. However, implementation complexity and performance depend on balance, used in file systems and databases. Graphs consist of vertices and edges connecting them. They can be directed or undirected, weighted or unweighted. Graphs model complex relationships and are flexible in structure. Implementation and traversal can be complex with higher memory usage. Used in social networks and route planning. Hash tables store key-value pairs using a hash function to calculate an index. They provide very fast data access and efficient searching, insertion, and deletion. However, collisions must be managed, and performance depends on the hash function quality, used in dictionaries and caches. Each data structure serves specific purposes. Arrays and linked lists handle linear data, stacks and queues manage ordered processing. Trees and graphs handle hierarchical and relational data, while hash tables offer fast key-based access. Understanding these structures allows selecting efficient solutions for problems. Linear data structures store data in sequential order. Arrays, lists, linked lists, stacks, queues, sets, and dictionaries are examples. Each element has a predecessor and successor, except the first and last. They allow straightforward traversal, ideal for problems requiring ordered data processing. Non-linear data structures do not store data sequentially. Trees and graphs are examples of hierarchical and network-based structures. They represent complex relationships and allow multiple connections. Ideal for problems requiring hierarchical or network modeling, more complex to implement and traverse. The choice of data structure impacts algorithmic performance. It affects both time and space efficiency. Different structures support operations at varying speeds. Choosing the right one is crucial for optimal execution. A core design decision, not an afterthought. Time performance refers to how long an algorithm takes to complete. Different data structures support operations like searching, inserting, and deleting at different speeds. For example, searching in arrays takes linear time, while in hash tables, it takes constant time. This difference is crucial for large datasets. Space usage refers to memory required by a data structure. Arrays use contiguous memory, making them efficient but potentially wasteful. Linked lists need extra memory for pointers, increasing usage. Dictionaries and sets require space for hash tables. Trees and graphs need space for node relationships. Considerations include operation types, dataset size, and access patterns. Memory constraints and scalability are also crucial. Choosing the wrong structure can slow execution and increase memory usage. Performance changes as data grows. Efficient design requires careful structure selection. Understanding data structures leads to algorithm analysis. Time and space complexity measure performance. Formal analysis is essential for designing efficient solutions. This foundation is crucial for scalable software. Next, explore algorithm analysis in depth. Arrays offer fast access, while lists provide flexible sizing. Linked lists allow easy insertion, and stacks support reversing operations. Queues ensure fair processing, and sets enforce uniqueness. Dictionaries offer fast lookups. Trees enable efficient searching, and graphs model complex relationships. Explore ebooks and journals for more on data structures. Recommended readings include works by Corman, Goodrich, and Knuth. These resources delve deeper into algorithms and data structures. They provide additional insights and examples. Enhance your understanding by exploring these materials. Correct. Refer to the ebooks and journals on the Moodle for this unit. For queries, email learnerwork at UK Versity. Submit assignments within 2 weeks after unit completion. Ensure compliance with submission guidelines. Stay engaged and continue learning. In conclusion, the video has provided a solid foundation in essential data structures and their applications. It highlights that choosing the appropriate data structure is crucial for efficient algorithm design, as it directly affects performance and memory usage. If you need any help, just WhatsApp 074843616888. Our team is always ready to assist. Thank you for your attention, and we look forward to seeing you in the next session.